Okay, so I want you to imagine something for a moment. Picture yourself stepping into, I don't know, one of the most important scientific archives in the world. Let's say the French National Library in Paris.
And you're not there to see some ancient, dusty book. You're there to see a specific set of artifacts, personal notebooks, handwritten over a century ago.
But these notebooks are so dangerous, so inherently radioactive that they have to be kept sealed inside lead-lined boxes.
That's right. These are Marie Curie's lab notebooks from around 1899. They're still fiercely contaminated with radium-226. If you want to see them today, you literally have to sign a liability waiver and put on full protective gear.
It's the ultimate physical proof, isn't it? That a scientific breakthrough, no matter how brilliant, can leave a permanent, dangerous trail.
It perfectly captures the story we're getting into, the sheer power and the deep peril, all in one.
And that image, a priceless piece of history that's also a radiological hazard, that's the core of our deep dive today. We want to understand where that power came from. I mean, how did two scientists who were, struggling for funding and working in a horrible, dilapidated shed in Paris manage to isolate radium? An element so potent it's still glowing in her notebooks.
We're going to trace that whole improbable path.
Yeah.
And it's a story that relies just as much on Marie Curie's incredible intellectual rigor as it does on, well, a massive industrial accident. A huge pile of what everyone thought was worthless Austrian mining waste.
So we'll get into the science, the methods, but also the surprising political context. And then we have to confront the devastating human cost of it all, from the factory floor right up to the discoverer herself.
It's an incredible story of triumph and tragedy.
Okay, so let's unpack this. Our story today, our deep dive, it doesn't actually begin with the Curies. It starts a little earlier in 1896 with a discovery that was, frankly, kind of a scientific footnote at the time.
Right? He was completely overshadowed by something much more dramatic. The big news, the thing everyone was talking about, was X-rays. Wilhelm Röntgen had just discovered them, and they were a sensation.
You could see bones inside a living person. It was spectacular.
Exactly. And in that context, you have this French physicist, Henri Becquerel. He was completely preoccupied with X-rays, and he had a hypothesis. He thought that maybe phosphorescence, that property where some materials glow after you expose them to light, was somehow connected to X-ray emission.
So his thinking was, shine sunlight on something like uranium salts and maybe they'll glow and give off X-rays.
That was the idea. But the real breakthrough, the world-changing moment, was pure accidental luck. It was driven by the weather in Paris, of all things.
Oh, of course.
In February of 1896, he was all set up to run an experiment, but the sun never came out. It was just gray and overcast. So he wrapped up his setup, a sample of uranium salts on a photographic plate with a little copper cross between them, and just stuck the whole thing in a dark desk drawer.
Waiting for a sunny day.
Right. But after a few days, he developed the plate anyway, and he found this clear, sharp image of the copper cross. The plate was blackened.
Meaning the uranium had been emitting some kind of penetrating rays all on its own, no sunlight needed.
Completely on its own. No external stimulus at all. He called them Becquerel rays, and he proved they were an intrinsic property of uranium. But here's the critical thing. The scientific world was still obsessed with X-rays. These Becquerel rays were weak, they were subtle. Frankly, they were boring compared to the excitement over medical imaging.
And this is exactly where Marie Curie comes in. She's looking for a topic for her doctoral thesis. So why, in the middle of this huge X-ray craze, did she decide to focus on these weak, boring uranic rays?
That choice tells you everything about her as a scientist. She wasn't chasing the spectacle, she was chasing the fundamental principles. She saw that these rays were completely misunderstood, and she sensed a major discovery was hiding there.
But to study them, she couldn't just use Becquerel's method. A photographic plate just tells you yes or no, the rays are there or they aren't. It's qualitative.
Exactly. She needed to be quantitative. She needed precision. She had to turn this vague observation into hard, measurable numbers. And that is the first great intellectual leap of her work.
The Curie method. And it all hinges on this one amazing piece of equipment. The piezoelectric electrometer.
It's probably the single most important piece of technology in this whole discovery. The science behind it is that when radiation passes through air, it actually knocks electrons off the air molecules. It ionizes the air, turning it into a conductor.
And if the air becomes a conductor, you can get a tiny electric current to flow through it.
A tiny, tiny current. And measuring that is the whole challenge. This wasn't the age of digital electronics, This was delicate precision engineering.
So how did this electrometer work? What was the setup?
It was an instrument adapted from earlier work that Pierre Curie had done with his brother Jacques. The heart of it was the ionization chamber. Think of it as a little sealed box. You put your radioactive sample inside, between two metal plates. As the sample radiates, it ionizes the air, which generates a current between the plates.
And the strength of that current is directly proportional to how radioactive the sample is.
Precisely. But you still have to measure that tiny current. And that's where the second part, the really ingenious part, comes in. The piezoelectric quartz balance.
This sounds complicated.
It's brilliant in its simplicity, really. Piezoelectricity is a property of some crystals, like quartz, where if you squeeze them or apply pressure, they generate an electric charge.
Okay.
The Curies flipped that on its head. They used known, measured weights to apply a precise amount of pressure to a quartz crystal. This generated a precise, known electric charge that they directed to flow against the current from the ionization chamber.
Ah, so it's a compensation system, like a perfect balance scale, but you're balancing invisible electric currents instead of weights.
That's a perfect analogy. The operator would literally add tiny weights to the quartz balance until the two electrical forces perfectly canceled each other out. They'd watch a little needle, and when it hit zero, they knew it was balanced.
And the amount of weight they had to add to the quartz gave them a precise numerical value for the intensity of the radiation.
Yes. For the first time, radioactivity wasn't just an observation. It was a number. It was quantifiable data.
That's just an extraordinary level of sophistication for the time. And it's this quantitative rigor, these hard numbers, that led directly to her fundamental hypothesis, right? The one that changed our whole understanding of matter.
Immediately. She measured all sorts of different uranium compounds, pure metal, various salts, powder, solutions, and her numbers were consistent. The intensity of the radiation depended only on the amount of uranium present.
It didn't matter what chemical form it was in.
It didn't matter at all. It could be a solid, a liquid, bonded with oxygen, whatever. That led her to the critical deduction. Radioactivity isn't a chemical reaction between atoms. It must be an atomic property. The radiation is coming from inside the atom itself.
And that was a revolutionary idea. At the time, the atom was seen as this indivisible, unchanging little ball.
Right. The idea that something could be spontaneously happening inside the atom, that it had an internal structure and energy source, that was radical.
And she got the physical proof for that radical idea almost immediately. This is where we get to the core anomaly, the big mystery.
Yes. After testing all these pure compounds, she started testing natural ores. And when she put a chunk of pitchblende, the dense black ore that uranium is extracted from, into her electrometer, she found something that just didn't make any sense.
The raw ore was more radioactive than the pure uranium she could get out of it?
Much more. Far more. Her data showed that a sample of pure metallic uranium would register about, say, 24 intensity units on her machine. But a sample of raw pitchblende, especially the good stuff from the Yakimov mines, tested at 83 units.
Wait, so the raw rock was almost 4 times more active than its most active known ingredient.
Exactly. And for a scientist like Marie Curie, who trusted her quantitative data above all else, that wasn't a small margin of error. That was an intellectual earthquake. It was a glaring, reproducible paradox.
And there's only one possible conclusion you can draw from that, isn't there?
Only one. If radioactivity is an atomic property, and this ore is 4 times more radioactive than the uranium in it, then there must be another unknown, undiscovered element in that ore, an element that's incredibly radioactive.
And that single observation, proven by her electrometer, basically launched the most important chemical hunt of the 20th century.
It's the moment everything changes. And it's when Pierre Curie puts aside his own research on crystals and joins Marie full-time. They're not just studying a phenomenon anymore. They're hunting for new elements.
Which brings us into the breakthrough year of 1898. They're now pioneering this new field we'd call radiochemistry.
That's right. They're combining traditional, messy, hands-on analytical chemistry with their high-precision electrometer. They would take the pitchblende, dissolve it, and separate it into different chemical fractions. Then they test each fraction.
So the electrometer was like a Geiger counter in a way. It was guiding them, telling them which beaker was hot.
It was their analytical tracer. And the first new element they tracked down came in July of 1898.
Polonium.
Polonium. They found it was concentrating alongside the element bismuth during the chemical separation. And its activity was just remarkable, about 400 times more active than uranium.
And the name she chose, polonium. That was not a subtle choice.
Not at all. It was a deeply political act. Marie named it in honor of her homeland, Poland, or Polonia in Latin.
A homeland that didn't technically exist on any map at the time.
It was partitioned, carved up between the Russian, Prussian, and Austrian empires. So for her to use the platform of international science to put the name of her country into the prominent record of the periodic table, it was an incredibly powerful statement. She was fighting for Polish independence from a laboratory in Paris.
But the discovery of polonium itself was a bit tricky, wasn't it? They couldn't actually isolate it in a pure form right away.
That's right, and it led to some controversy. A German chemist named Mark Band later isolated a radioactive substance he called radiotellurium, and there was a dispute over whether it was the same thing. The problem, as they'd later learn, lies with polonium itself.
What's the issue?
It has a really short half-life. The isotope they were working with, polonium-210, has a half-life of only about 140 days. That means its activity just drops off really quickly. So you can imagine them trying to isolate it, and their sample is literally disappearing as they work.
It's a race against atomic decay.
A race against the clock.
Yeah.
But the element that truly defined their legacy, the one with the absolutely astronomical activity, came just a few months later.
Radium.
Radium. They announced it in December of 1898. This one was found concentrated in the chemical fraction with barium. And if polonium was 400 times more active than uranium, their initial estimates for radium were that it was nearly 900 times, and in its purest form, maybe even 1,000,000 times more active.
1,000,000 times. That's a staggering number. But it presents a huge practical problem. If this stuff is so active but exists in such tiny quantities, how do you get enough of it to prove it's a new element? You can't do that with a few grams of ore.
No. You need tons of it. Literally, tons. And that would have been completely impossible for them. They were broke, working in a shed. They couldn't just buy a trainload of expensive ore.
And this is where the story takes this incredible turn, where the sheer accidental luck of industrial history steps in.
This is the fortuitous industrial pre-concentrations, the key to the whole thing.
Okay, so tell us about the source. Where did this material come from?
It came from the Jakimov mines in Bohemia, which was then part of the Austrian Empire. But the key isn't that the Curies found the mine. It's that the mine had been operating for decades for a completely different reason.
This is what you call the 40-year accident. What was this factory at Jakimov actually trying to make?
For about 40 years, since 1853, the Imperial and Royal Uranium Factory there had one job: producing uranium yellow.
Uranium yellow.
It's a chemical called sodium diuranate. It's a vibrant yellow pigment they used primarily for coloring glass and ceramics. If you've ever seen that beautiful old greenish yellow glass that glows under a black light, that's uranium glass. The factory was mining this powerful ore for its color.
So they were only interested in the uranium. They processed the pitchblende ore to leach out the uranium yellow pigment.
Precisely. The chemist there, Adolf Patera, had developed this process. They'd treat the ore and use various chemicals to dissolve and pull out the soluble uranium compounds. That was the valuable product.
And everything else was just waste.
Everything else. After they extracted the uranium, they were left with this enormous pile of sludge-like, insoluble residue. And for 40 years, it was officially classified as worthless waste. It just piled up.
But this worthless waste was the most valuable thing in the world to the Curies. Why? What was the chemical stroke of luck?
The luck is all in the chemistry of the waste. Radium is an alkaline earth metal, which means on the periodic table, it behaves a lot like barium. They're chemical cousins. So when Patera's process was designed to pull out the soluble uranium, it left behind the highly insoluble things. And it just so happens that the sulfate forms of barium and radium are extremely insoluble. So the radium, chemically bonded with the barium, got left behind in the waste pile.
So the industrial process, completely by accident, was acting like a giant filter. It was removing the uranium and leaving behind a concentrated sludge of barium and radium.
It was a radium pre-concentrate. The very first step of their Herculean task had already been done for them on an industrial scale, for free, for 40 years.
And that's why the Austrian government was willing to just give it to them.
They literally saw it as getting rid of their trash. They gave the Curies an initial 100 kilograms for free and later sold them metric tons of it for just the cost of shipping. They were practically paying the Curies to haul away the key to the atomic age.
That is just an unbelievable stroke of fortune. So now they have the raw material, and this is where the real back-breaking labor begins.
The Herculean labor of isolation. This process took them 45 months, almost 4 years. And the conditions they worked in were, well, they were horrific.
We hear about the shed, the drafty, leaky former dissection room. Can you really paint a picture of what that was like?
Marie's own notebooks do it best. She complains about the miserable cold, There's one entry where she records the temperature inside the shed as 6.25 degrees Ciela with 10 exclamation points.
6 degrees Celsius, that's about 43 degrees Fahrenheit.
Yes, freezing. It was unheated, the roof leaked, and they were performing what was essentially industrial-scale chemistry, breathing in toxic fumes day in and day out.
This wasn't clean, precise lab work. This was heavy physical industry.
Oh, absolutely. The scale of it is just mind-boggling. To get just 1 decigram, that's a tenth of a gram of pure radium, they had to start with about 1 ton of that pitch blende residue.
A ton of sludge to get a pinch of powder.
They were processing it in 20-kilogram batches. Marie described carrying these huge vats of boiling solution, stirring the bubbling sludge with an iron rod that was almost as tall as she was, for hours, for days, for years.
And what was the central chemical challenge they were trying to solve with all this boiling and stirring?
It all came down to one thing: separating the radium from the barium. As we said, they're chemical twins. They behave almost identically. So they had to find and exploit one tiny subtle difference between them.
And that process is called fractional crystallization?
Yes. The principle is based on a tiny difference in solubility. It turns out that radium chloride is slightly less soluble than barium chloride in a hydrochloric acid solution.
Less soluble, so that means it crystallizes out of a solution a little bit more easily.
Exactly. So what they would do is take a batch of the mixed chlorides, dissolve it in boiling water, and then let the solution cool down. As it cools, the crystals start to form. And the very first crystals they precipitate out of the solution are slightly more enriched in radium.
And the barium, being a bit more soluble, tends to stay behind in the liquid, the mother looker, as they called it.
That's it. And then the process becomes one of relentless, painstaking iteration. You take those slightly enriched crystals, you dissolve them again, you recrystallize them, skim off the new, even more enriched crystals, and move them to the next stage of purification.
And they had to repeat this process. How many times?
Thousands of times. It was a cascade of purification, moving the increasingly radioactive material from vat to vat, each step making it a little bit purer, a little bit more concentrated. It was physically brutal and methodologically meticulous.
But without that final pure sample, the scientific world wouldn't have accepted their discovery. They needed that definitive proof.
And in 1902, after nearly 4 years of this labor, Marie finally succeeded. She isolated a tenth of a gram of pure radium chloride. She was able to measure its atomic weight, 226.45, proving it was a unique element, distinct from barium.
And the final piece of the puzzle.
The final confirmation came from a spectral analysis by a man named de Marseille. He analyzed the light emitted by her pure sample and found new, distinct spectral lines that had never been seen before. That was it. Radium was real.
The physical proof was secure. And this is where we move into the consequences. The isolation of radium didn't just win them awards, it fundamentally changed science.
It did. It proved her initial hypothesis beyond any doubt that radioactivity was an intrinsic property of the atom and that you could use this property to hunt for new elements.
And this work immediately became the foundation for the next huge conceptual leap, which came from Ernest Rutherford and Frederick Soddy.
Their theory of atomic radioactive transformations, or what we now call atomic disintegration. Before the Curies, the atom was seen as permanent, immutable. Rutherford and Soddy, using the Curie's work, proposed that atoms are not stable. They undergo continuous transformation, breaking down from one element into another.
So radium wasn't just sitting there glowing passively, it was actively decaying into something else.
Exactly. And the most direct proof of this was the observation that radium spontaneously produces the element helium. The alpha particles it was emitting were identified as helium nuclei. This was elemental transmutation, the dream of the alchemists, happening right there on the lab bench.
It's no surprise that this work led to the highest honors in science, the Nobel Prizes.
The first one came pretty quickly, in 1903, for physics. It was shared with Becquerel and with Pierre. But there's a fascinating and ugly backstory there.
The committee initially tried to exclude her, didn't they?
They did. The nomination was just for Becquerel and Pierre Curie. It was blatant gender bias.
And it was Pierre who stepped in.
He took a firm, principled stand. He wrote to the committee and insisted that the research was a true collaboration and that it was impossible to consider the work on radioactivity without recognizing Marie's central role. His intervention was crucial. It secured her place, and she became the first woman ever to win a Nobel Prize.
And then she did it again. In 1911, she won the Nobel Prize in Chemistry, this time all by herself, for the discovery and isolation of radium and polonium.
Which makes her the only person in history to this day to win Nobels in 2 different scientific fields. It's an absolutely unparalleled legacy.
But there's another part of their legacy that's just as important, their decision about what to do with the discovery.
Their scientific altruism. They made a very conscious choice not to patent the process for isolating radium.
Which, when you think about the immense effort they put in and the immediate value of radium, was a massive financial sacrifice.
It was huge. Pierre famously said something like, "Radium is an element. It belongs to everyone." They felt that since their work was for the benefit of humanity, the knowledge should be freely available. A noble choice.
But a choice that had, well, complicated and ultimately tragic consequences. By not patenting it, they allowed a global radium industry to just explode, with no controls, no standards, and no real understanding of the dangers.
And the discovery of those dangers, the biological effects of radium, was yet again completely accidental.
Right. Henri Becquerel, back in 1901, he was carrying a small glass tube of radium in his vest pocket.
And it gave him a severe skin burn, a deep lesion that took a long time to heal. That was the first clue that this invisible energy could destroy living tissue.
And Pierre Curie's reaction to this is just, to me, staggering. He deliberately replicated the experiment on himself.
He did. He strapped a sample of radium to his own arm to conduct a controlled experiment on its destructive power. The resulting wound took months to heal, but it gave them the key insight. If this stuff destroys healthy tissue, maybe it can be used to destroy unhealthy tissue, like tumors.
And that's the birth of Curietherapy, what we now call brachytherapy, placing a radioactive source right next to a cancer to kill it. It was one of the very first effective cancer treatments.
Used as early as 1903, radium instantly became this miracle substance in the public imagination.
And this is where the story pivots hard. From cure to curse, the hype just completely outran the science. It was marketed as a panacea, a cure-all for everything.
The commercial frenzy was insane. You could buy radium-laced chocolate, toothpaste, face creams, you name it.
But what was the most dangerous, the most infamous example of this?
Without a doubt, it was a product from the 1920s called Radithor. It's basically just distilled water with at least 2 microcuries of dissolved radium in every little bottle. It was marketed as perpetual sunshine.
And people were just drinking it.
Drinking it daily. It was sold as a tonic that could cure over 150 different ailments, from high blood pressure to impotence. It was the ultimate snake oil, but with a radioactive ingredient.
And this continued until the tragic case of Eben Byers.
The wealthy Pittsburgh industrialist. He injured his arm, and a doctor prescribed Radithor. He got hooked on the stuff, thinking it gave him energy. He ended up drinking something like 1,400 bottles of it over several years.
And the result?
It completely destroyed his body from the inside out. The radium deposited in his bones and literally ate away at his skeleton. His jaw disintegrated. He died a horrific death in 1932 from radiation-induced cancers. His case was so gruesome, it finally shocked the public and led to federal regulation.
That commercial craze, however, it fueled a massive industrial demand for radium, especially in the U.S. during World War I. And this brings us to the great American tragedy of the story, the Radium Girls.
Right. The military needed luminous paint for everything. Glow-in-the-dark gun sights, airplane instrument panels, watches for soldiers in the trenches. The demand exploded.
And the center of this industry was the U.S. Radium Corporation in Orange, New Jersey.
From 1917 to 1926, they employed hundreds of young women as dial painters. It was seen as good work for women at the time. It paid well, and it was considered delicate, almost artistic work, painting these tiny numbers.
And the core of the tragedy was the technique they were taught to use.
The company insisted on a technique called lip pointing. To get a super fine point on their tiny camel hair brushes, they were told to put the brush tip between their lips and shape it with their tongue.
So with every single number they painted, they were ingesting a small dose of radium paint.
A small but lethal dose. And radium, being chemically similar to calcium, goes straight to the bones. It incorporates itself into the skeleton, and it just sits there, irradiating the person from the inside for the rest of their life.
Their own bones became radioactive.
Their bones were literally glowing in the dark. The symptoms were horrific. It started with anemia, severe dental problems. Then their bones would become brittle and break without any cause. And then came the most infamous condition, radium jaw. A grotesque, painful necrosis where the jawbone would literally rot away.
What's so infuriating is how long the company denied responsibility. They tried to claim the illnesses were unrelated to the work.
It was a calculated campaign of denial. But we know from federal records that the company was aware of the problem almost from the beginning. Investigators from the Department of Labor were documenting severe illnesses in workers as early as 1917, proving a direct and rapid link.
So they were collecting data showing their workers were getting sick while publicly saying the paint was harmless.
Worse than that, they actively suppressed evidence. They commissioned a study from a team at Harvard, but when the report came back confirming how dangerous the conditions were, U.S. Radium threatened the scientists with a lawsuit to keep them from publishing it.
It's just astonishing corporate negligence. And the women had to fight for years to be heard.
They did. The company tried to smear their reputations, claiming they were sick for other reasons. The legal battle of the 5 Radium girls, led by Grace Fryer, is an iconic story of perseverance. They were dying, their bodies were falling apart, but they kept fighting.
And they eventually won a settlement, didn't they?
They did. In 1928, it was a landmark case. Their struggle established the right of individual workers to sue their employers for damages from occupational diseases. It forced the creation of the very first health and safety standards for handling radioactive materials in the U.S. Their tragedy directly built the foundations of modern industrial hygiene.
And so the story of this element, born from waste, comes full circle to the tragedy of its discoverer. We started with Marie Curie's radioactive notebooks, and her own body paid the ultimate price.
She died in 1934 at the age of 66. The official cause was aplastic anemia, a bone marrow disease. It was, without a doubt, caused by her decades of unprotected exposure to radiation.
She used to carry vials of radium in her pockets just to see them glow. She described the beautiful blue glow of the substances in her lab at night. She saw it as a wonder, not a cumulative poison.
And the irony is just profound. She gave the world a tool to fight cancer, and she died from a radiation-induced disease caused by the very element she discovered. Her sacrifice wasn't a single event. It was a slow, invisible accumulation of damage over 30 years.
And that brings us back to those physical relics. Her notebooks, her personal effects, even some of her cookbooks are still dangerously radioactive today.
The main contaminant is radium-226, which is an extremely persistent isotope.
How persistent are we talking here? What's the half-life?
The half-life of radium-226 is about 1,600 years.
1,600 years. So in the year 3600, her notebooks will still be half as radioactive as they are today.
That's right. They will remain hazardous for millennia. Dozens of generations from now, the evidence of her work will still be physically dangerous.
It's a stunning physical testament to her discovery. Stored in lead boxes, requiring a waiver to view, it is literally history that can still harm you.
The whole story of radium is that duality. The genius of Marie Curie, who proved the atom wasn't immutable and gave us radiotherapy, set against this immense trail of human suffering, from the mines to the factories to her own body.
It really is the ultimate story of a scientific breakthrough, just running far ahead of our understanding of how to protect ourselves from it. That element, pulled from industrial trash, became one of the most valuable substances on Earth, but it revealed its true destructive nature far too late for so many people. And that leads us to our final thought for you to mull over. The fact that accessing the history of this foundational science requires lead shielding and a liability waiver. It means the cost of that discovery is still being paid today, so it makes you wonder, what other invisible costs of our modern scientific progress, whether they're hidden in our biology, our digital world, or our environment, are we absorbing right now simply because the breakthroughs have once again run far ahead of our wisdom?